Hello students, I'm your lecturer Funman for this experiment in CM2191, the Grignard reaction. There are a few objectives for this experiment. Number one, it is to synthesize a carboxylic acid from a bromide using a Grignard reaction. Here we are trying to help you, not just any random bromide, but it's an ARA bromide. Second, you need to purify the product using recrystallization. Remember that we have two kinds of recrystallization, single solvent or solvent pair, both of which you have done last time in CM1191. If you're not too familiar, it's good to revise again on the videos recorded on the YouTube. I'll show the link, and this presents you a good chance to practice again. Know the difference. I think it's very important. And last objective, it is to identify the product using the melting point analysis. Alright, so this time we are going to perform a Grignard reaction. Now, a little background introduction on this Grignard reaction, which is so famous as a chemist, you ought to know this very well. Now, Victor Grignard was awarded the Nobel Prize in Chemistry in 1912 for the discovery of the Grignard reagent. And from then on, the Grignard reactions have been widely used in organic synthesis due to the simplicity in carrying out the experiments. The reactions are so straightforward, and they have been used broadly in medicine synthesis or in the pharmaceutical industry for materials. So a Grignard reagent is represented by a general formula of RMGX. Next time when somebody say RMGX, you know what this is, a Grignard reagent. So R is like an alkyl group or aryl group, and X is a halogen, which normally we use chlorine, bromine, or iodine. You should think of why we never use fluorine or even astatine. Think about it. Now, the carbon-magnesium bond in a Grignard reagent is not purely covalent, but it is highly polarized due to the difference in the electronegativity between the magnesium and the carbon, so it makes the carbon center highly nucleophilic. What happens is, before you add the magnesium inside, it was just an alkyl halide, Rx. You look into the carbon-halogen bond. Carbon is less electronegative than the halogen, so it takes a delta positive. But right now you insert the magnesium, and magnesium is the most electropositive among these three elements, Mg, carbon, and halogen. So Mg must take the positive charge, leaving behind the negative charge to the carbon and the halogen. Now this bond here, the CMG bond, right, is partially covalent and partially ionic. So it's a bit here and there, and that's why it's very reactive. So one of these many applications of a Grignard reagent, it is a reaction with a carbonyl functional group. As we know, carbonyl group means it has a CO double bond, and because of this bond that's polarized, the carbon there takes a delta positive charge that attracts nucleophile, nucleophilic addition. So what are the groups that contains the carbonyl CO double bond? Carbon dioxide, aldehydes, ketones, or esters. And Grignard reagents react with these groups to form carboxylic acid, secondary or even tertiary alcohol. For the case of the reaction with CO2, aldehyde, ketones, only one equivalent Grignard reagent is used to involve a direct nucleophilic addition reaction. But in the reaction with an ester, two equivalents of the Grignard reagents are needed for two consecutive nucleophilic addition reactions. Now in this experiment you are doing, a Grignard reagent is prepared from the ARA bromide A, which you are supposed to find out what is this, and magnesium. And then the Grignard reagent B that's being formed is added to dry ice, CO2 here, to give a carboxylic acid C. Now for the safety precautions, we know that we'll be using concentrated hydrochloric acid. This is highly corrosive, iodine is very corrosive, and dry ice cause severe cryogenic burns. So you have to handle these chemicals well, bravely but safely. Wear your gloves, the nitrile gloves, all the time. Do not take off your goggles once you are inside the lab coats as well. Wear high ankle socks, protect your ankles and feet. Tetrahydrofuran, the THF, and ethanol are highly flammable. Magnesium is flammable. We know we come from group 2, the alkaline earth elements. They are used as fireworks, of course they're flammable. And calcium chloride, THF, iodine, all these are irritants. So contact with these substances without gloves should be avoided. THF tends to form peroxides more readily than normal ether, and these peroxides are explosive. And dry ice can cause cold burns. And chloroform D is carcinogenic, so please do not inhale them or allow them to contact your skin or eyes. And perform all the operations in a well-ventilated fume hood. And of course refer to the MSDS, or nowadays they call it SDS, of the chemicals used for detailed safety information. Right, you got to check out what are the properties, good and bad, of the chemicals you'll be using, at least the boiling point, melting point, density. We are chemists. So, you'll be given one of these 4 substrates, the Ara bromide. And you need to test from the melting point at the end of the reactions for your product and decide which of these was the starting material. So you can't rely on us telling you the answer. We are not going to tell you. You need to find out from qualitative analysis. Okay, so pretty much you're having a Grignard reagent here. You need to make it first. We won't give you because we would like you to try to make the Grignard reagent. So how do you make the Grignard reagent? First of all, you take an alkyl bromide that we provide for you. You add some fresh magnesium and throw in some iodine. In THF, tetrahydrofuran is a solvent. There is polar aprodic solvent, and that's how you form the Grignard reagent. And the second part of this experiment is to add your electrophile, in this case is carbon dioxide, in the form of dry ice. And after which, at the end of the reaction, you protonate it using the acid to get back your carboxylic acid. So for these 4 different products that you could be getting, these are the melting point range that I've shown you. And one good thing to note is, why do they have such a melting point range? You compare these 4 substrates that you have. Why is it that the 1,4-disubstituent will have the highest melting point range, and whereas the monosubstituent will only have a lowest melting point range? It's good to think why. Could that be intramolecular hydrogen bonding? What is it? Students are always confused the correlation between the melting point and boiling point. They're the same, but they are not. Both utilizes van der Waals forces of attraction, intermolecular forces. How strong these molecules, the same molecules, are being held together, right? But the thing is, in boiling point, we are talking about the conversion from a liquid state to a gaseous state. That means the particles are further apart. But in solid state, we are trying to see how easy or difficult to mobilize the molecules from a rigid crystalline structure into a liquid form that's a bit more fluid. So there's a bit of difference. So melting point also regard the packing structure of the molecule. So if the molecule is very polar, but then it doesn't pack very nicely, so it's not worthy of a high melting point, because you find gaps between the molecules. You know, there are gaps, right? Gaps means what? There are you don't have a capacity for short range forces of attraction. And recall that these are weak attraction forces, so we need to get them close together to interact using electron cloud, your induced dipole, instantaneous dipole, or some people call it a London force. You know, you can't leave any gaps. The more gaps you have, the weaker the IMF. I'm sure all of you played something like this before in your childhood, the game called Tetris, right? If you have, you know, there are a few blocks, right, that you can get coming from the top, right, the debris. So you have those 4 cube in one line. That's the best because you can always align it, you know, any way you like. Then there's one that's L shape, okay, L shape, and there's one that's a box, you know, a square shape, and then there's lastly the Switzerland, the cross, right? We all dislike the cross because it's very hard to pack the cross. You get it? Because when we have crosses, we only have it's not very easy not to leave any gaps. So packing, remember, melting point talks about packing as well as the amount of dipole forces that exist. Right, so there are 3 parts for this procedure. Part 1 will be the preparation of the Grignard reagent. You're going to make it yourself. So we talk about the setup and the reflux conditions involved. And then part 2, reaction with the CO2. How do you put the CO2 inside? Do you blow it from a mouth? We have CO2, right? Breathing, respiration, but we don't do that. Why do we have to acidify the workup? And part 3, we need to purify our substance. In most synthesis reaction, there will be impurities. You can't help it. You can't help it. So one way we can purify our compound is, remember, to do a column chromatography. But in this case, this time around, we're going to do a recrystallization. Solvent pair, ethanol and water. It's also good to think about in your synthesis in this procedure, we know that, Grignard reactions, we need it to have a dry environment. But then you got to think, is it all the steps involved must be dry, or is it certain steps that are more pertinent to the Grignard reaction that you need? And it's also good before you start the synthetic reaction to predict what could be the side products that you could get if you're not being very careful, or if you added too much of certain reagent, let's say A or B, and then you may have one in excess. And if you did not allow the reaction to finish, that means you end it prematurely, what could you get instead? Good to think about it. Like maybe you see here, let's say this is a Grignard reagent. You are supposed to throw in and react with CO2, then add acid. But what if you add CO2 and then add acid too fast, too soon? You still get this, right, the acid, but what are the side products or impurities that you suspect may be contaminating your product? So how do you prepare a Grignard reagent? Of course, you need to set up a very dry atmosphere. So for the setup, you need a 2-neck round bottom flask and a stirring bar. We know that the two kinds of stirring bar, one is a flat one, one is a round one. So in this case, you ought to know which one you should be using because you're using a round bottom flask. And of course, you need a reflux condenser. Think about what is the solvent used, THF, tetrahydrofuran. It doesn't have a very, very high boiling point, so the reaction is quite exothermic, and of course you need to heat up the reaction mixture. And if you do not use a reflux condenser, what might happen? All your solvent vaporize, and would that be desirable? Okay. And next, you also need a dropping funnel. Take note, this kind of glassware is also good to research on why do we use a particular kind of glassware for certain reaction. Dropping funnel, or some people call it a tissue funnel, is mainly to contain substance that's a bit more hygroscopic, that doesn't like to have moisture involved, because once you contact with some H2O in the air, it will be gone. It will react away with the water, and then you do not want that to happen. You want that particular reagent to react with what's inside the RBF and not outside. So you're going to trap it inside first in a dropping funnel, and then see on the top you have something called a guard tube. Not sure whether it's the first time doing it, but guard tube is very common in organic synthesis. We put some hygroscopic drying agent inside, in this case calcium chloride. So these absorb moisture, and then we seal it with some cotton wool. So in case the air, right, you have H2O, high humidity going in, then the first part, the guard, will be the calcium chloride. You just grab all the water and disallow them from entering your reaction, saving it. This saves our life. And why do we need two? We need two because there are two exit potential outlets for the reaction here, one coming from the condenser, vertical one, and from a tissue funnel. So you should understand why we should not wash any glassware for setup, because we want to be dry. Come on, it's Grignard reagent. Next thing to pay attention to is set up the reaction from the bottoms up, right? Just like you drink, bottoms up. Why so? Because I am making use of gravity. Make it your friend. Gravity is on your side. You secure your RBF first using the clamp and ball's head, adjust it right, and then you let your condenser sit through, leaving behind no gaps. If you fix from the top and then you adjust the RBF upwards, there may be some gaps inside, allowing oxygen, water vapor, among other reactive gases. Not good for you. You may not realize, you think it's all sealed, right? Nicely sealed. No, you never know. Okay, so always set up from the bottoms up to have an enclosed atmosphere. And don't forget, people always forget to add the stirring bar. So everything added, then they realized it's not stirring because they forgot the stirring bar. It happens many times. And what do they do? they need to restart everything again, they waste half an hour of their time, they feel frustrated, and then the mood goes down, you know. Happiness level, it just tumble all the way, and then that affect the results and emotions afterwards. Not good at all. So always prepare, right? Think through what you're going to do, what the experiment's going to do, the chemicals, how are they going to react. Think through all this, write down, jot down small notes. Do not just refer to that manual note and refer, okay, step 1, step 2, what do we take, how much. You should have it right here. Try your best, okay? It's a training. So after assembly, you should see something like this. Something like this. Okay, this is your tester funnel, and this part here, we don't call it a tap. Please don't call it a tap. This is called stopcock. You know, we have seen from year 1, right? Remember, Saprocci funnel, extraction, stopcock, right? And check for water flow, make sure there's no leaking. Sometimes the stopcock is loose. If it is loose, I want to stop the addition, but it's not doing so. That's really too bad because you started the reaction for an hour or so. How are you going to salvage it? Okay, so make sure it's not leaking. And next thing is, you need to check that the tubing is not clogged, and of course it's sealed to the condenser, because if it leaks, right, again water goes inside the flask. GG for you. So these are the things you have to check, you know. Don't just focus on one particular segment. You have to be very careful about everything that you set up. And for the procedure, you gotta weigh 20 millimoles of magnesium turnings. You have to convert, using the mole concept. What is the mass you have to take, because the weighing balance is not going to give you in mole. You have to use a weighing paper, then place one small tiny crystal of iodine onto the same weighing paper. Okay, you can read it yourself. Remove the condenser, add the magnesium turning and iodine to the round BF. Remove the dropping funnel from the setup, and then dispense, automatic dispenser, pre-adjusted volume of the unknown error bromide. Okay, and then THF, all goes in. Okay, and then so dispense the pre-adjusted volume of the error bromide. Okay, and then 10 ml of your anhydrous THF. Okay, into the dropping funnel. Then mix the contents by gentle swirling, just gentle, not too much because it flow out. And then put it back, let it sit nicely onto the neck, 2-neck RBF. Now then slowly turn on the stopcock and then add 3 ml of the error bromide solution from the dropping funnel to the magnesium turning, okay, while stirring. Now how do you know that reaction is starting? You can see that the iodine color, which was originally what? A bit purple, dark purple, almost black, will start to go off. Then you see some colorless solution, right? And a gentle warming, boiling of the solution. That means you may see some bubbles, boiling kind of observation. Then it's good to consider, like, why did that happen? Am I even heating the reaction mixture? Do we need to heat it up? Okay, so coming back to the general reaction of magnesium and alkyl halide, and we know that Grignard reagent is typically prepared by the reaction of an alkyl, aryl, RX, okay, Mg. We talked about it just now. And the solvent we use is like an ether. We never use methanol, ethanol, acid, no way. Think about it, why? Because these are protic solvents. We are going to have a very reactive metal here, Mg, that can potentially react and get displaced. You get hydrogen gas. You kill the Mg. No good. And for all these Grignard reactions, you can see that the initiation will occur within the first 10-20% by weight addition of the alkyl halide. And since we know the reaction is very exothermic, and then you can see that it is really starting, it is beginning. Now what happens if you add too much alkyl halide at the beginning? You just flush everything down, you're too nervous, you're too eager. Reaction becomes too rapid, too much heat being generated on the same site. And then those heat is going to boil your low boiling ether and vaporize it. No more solvent. What happens? You release the reaction mixture into the atmosphere. Pressure build-up, explosion. If there are cracks on the flask that you couldn't see, it's really dangerous. Really, really hazardous. Okay? So if you're not very careful, chemistry can be dangerous. So always check carefully. Don't just follow procedure and just take it so easily and pay no attention to anything. Now for Grignard reaction, what are some of the effects of external agents that are unwanted? Let's say water vapor, oxygen. Once you make your Grignard reagent, it is rather moisture sensitive, so you shouldn't get in contact with all this H2O, O2. Hence, the solvent must be dry. The solvent here we use THF that has an oxygen here in the 5-member ring. And we know that when you have oxygen, it can attract H2O. So of course we get the best grade for you, the tetrahydrofuran that's free of H2O, the best one, okay? So it contains less than 0.02% of H2O. If you go and search online on Sigma Aldrich, these are the chemical sites you purchase. Many kinds of THF, but which is the one that we prefer for synthesis? Analytical reagent, lab reagent, HPLC, high performance liquid chromatography, very high purity. Okay, then there's some stabilizer. So since we know that the Grignard reagent is so moisture sensitive, it is so reactive, super high energy, because now we're having a carbon taking negative charge. So it's always good to have a reaction performed in nitrogen or even argon in a glove box. Now, oxygen, it actually does not slow down the ionization, but it may react with the Grignard reagent produced. So sometimes in industry, when we want to produce a large scale of these Grignard reagent from the previous batch, batch-wise synthesis in the industry was added to the reactor. Why? Because we do not want to waste them, and some more they are reactive. We still need to get rid of them at the end of the day. So why not we just use them, react and recycle them? This is the industrial process. It's not like lab, where you do it just once, millimole. You have any excess, you do acid workup, okay, kill them, purify and done. In the industry, we're talking about tons. So when you translate to a bigger scale, it costs money. And those are profit-driven companies, so every single cent costs a little to them. Okay, so this we have gone through just now. So here we're going to work with aromatic halide. And for the magnesium, the reaction rate is directly proportional to the available metal surface area. So this is an organometallic synthesis. Now, think about why we need to use iodine in the first place. Why just a small amount? Why do we have to add that? Something called the passivation. We need to activate the surface of that magnesium. Magnesium, being very high in the reactivity series, it can be easily oxidized by the air. You get some oxides on the top, so that would not be so reactive compared to fresh virgin magnesium, and it may not go in between the carbon halogen bond. So we need to activate it, react it away, the MgO. So there are other ways of passivating the magnesium. We can use sandpaper, we know. Ionic MgO is brittle, so we can just scrape it off. We release a fresh surface of magnesium platform for the reagent to react onto the site. Another way is to add some activating agent such as 1,2-dibromoethane. A bit toxic, but it works pretty well. And then you just remove the layer. But in this case, you're using iodine, so a small piece will do. Don't add too much. So once the reaction has initiated, we know it's starting, okay? Very comforted. We need to add the remaining bromide solution dropwise. Again here, we notice dropwise because every drop we add is going to give off a lot of heat. You don't want it to build up and then pressure explode in the fume hood. It's very messy. Nobody like to clean up such a mess. And it's dangerous. And also we want it to have even stirring and make sure that every drop goes in, it reacts away. with the magnesium. We don't want to waste anything. Get a high yield, get a high purity. Replace the reaction flask in the water bath, cooling for a while, and then set the hot plate to about 100 degrees Celsius. So after some time, the heat will dissipate and you have no more heat. And of course, in most of the reaction, we need to overcome the activation energy. So we're going to supply some heat. In this case, we use a water bath. Why no direct heating? Safety. So you start the water flow in the condenser, vapor comes up, right? We're going to cool down the THF if they vaporize, and maintain the solution in general reflux until reaction is complete. And we try it many times, and it's about 50 minutes. So how do you tell if we do not give this clue to you, or because it varies from person to person? How do we know that the reaction is almost complete? Normally you can use TLC, right, to monitor the reaction progress. Okay, but here we know that we can tell from the formation of a clear or brown solution, and when all the magnesium has been used up, has reacted, it's all gone, dissolved. The next part, you take out your RBF and then you transfer it carefully using a spatula, right? Stir it, that contains your solid CO2, your dry ice. Okay, make sure it's broken down. You release a high surface area, small pieces, right? 20 grams, measure carefully. Again, do not be too greedy. 400 ml beaker, we need a larger one to contain it, to have more reaction site. As you transfer, stir aggressively, okay, but not to break anything. After stirring, until all the dry ice is gone, by virtue of sublimation or other means, then you add 50 ml of ice water to the mixture. This is like your workup. And why ice water? Why not just ordinary water? Cold. Reaction again is very exothermic, we want to cool it down. After that, you can feel it's very cold, ice water. Then you add corn HCl, okay, until it's very acidic. Because at the end of the Grignard reaction, you're going to have an anion inside the system. So without adding the acid, it's still going to be negatively charged. So you have to make sure that you protonic back the H+, and make sure you get the COOH. The carboxylic acid is your desired product. Okay, then how do you get it out? You do a vacuum filtration, suction filtration, right? Get rid of the solvents and collect the solid. But this is not pure yet. You're going to proceed to the next step, recrystallization. Okay, so we only collect the dry ice when you have cooled the reaction mixture with your Grignard reagent inside, okay, to RTP, room temperature first, and then you take it out and transfer to the dry ice. Do not be too hasty and collect CO2 already at the start. Then after you get ready and it's all gone, it's all sublime. For recrystallization, this is the preferred technique in the industrial process because it's safe, cheaper. Cost is always the thing about industry, and it can be done on a large scale. Imagine we do, or those guys in the industry in Jurong Island do column chromatography for several tons. I don't know how they survive. Now for recryst, the choice of solvent is the utmost importance. We need to select a solvent, okay, in which the solute has a maximum solubility in the hot solvent and minimum solubility in the cold solvent. So we know the solid can be polar or non-polar. We have two main categories of solvents here. High polarity solvent, ethanol, methanol, water. All of them have OH bond, that's why it makes them very polar. And those with low polarity solvent, toluene or metabenzene, flammable, oil light like petrol, ether, quite smelly, and ether acetate, and ester. Now for two solvent system, you are trying to mix two solvents. Why is two solvent better than a single solvent system for recryst? Take a look at this graph here. You have solvent A, B, and C. Which is the best solvent for recryst in this reaction? It must be A. Why is it the best solvent? Because you see, the gradient for the graph is very steep. We're going to have a gram soluble, the solubility against temperature. When we have a very steep gradient. It means that the solubility is very sensitive towards the temperature change. When we have a bit of increment in temperature, it becomes more soluble. When we have a bit less, it becomes very insoluble. So this is how we draw the line to see, okay, if I want to dissolve my impurities and then collect my pure compound at a certain elevated temperature. For C and B, they are poor solvents because if I increase the heat a bit, it still becomes very soluble inside. There's not much difference in the solubility, so you may precipitate both your impurity and your desired product. If you are introducing two solvents in the system, it's even better because you can play around with the proportion. You have more factor, and then the graph will not be even this. It may be more helpful to you. Go and research how it will look like. And it doesn't mean that you can anyhow choose two solvents. You need to make sure that these two solvents can mix. No point choosing oil and water, right? If they can't mix. You also have to ensure that your solute dissolves in both solvents. So two things. One is the solvents can be miscible in each other, and the second thing is your solute must be able to dissolve in both solvents. Procedure wise, you can read these words, okay, but what is easier is not to translate the words into your action, but to see the videos that we have done it for you. Then you try to recall the motion. I guess it's easier, and try to practice. But if you forget, fret not. You can watch the video using the NUS Wi-Fi first, and then you do the reaction, okay? Don't panic. Don't panic. Now after you are done, we need to avoid disturb the solution, okay, because they are trying to form crystals, they are trying to form a precipitate to grow a solid. So if you get the right amount by using a dropper, right, and then you disturb them, then you're shaking it, then it will dissolve again, so it's not going to help. So every time you do this, please do not disturb the hot plate or your flask. Yeah. One thing to note is you should use minimum volume of ethanol used for the second part when you're trying to dissolve all the solid. Okay, and when you perform all the steps in your synthesis, always think, what is the rationale of doing such steps? Don't just follow monkey see, monkey do without knowing why. Now lastly, I've mentioned that this is a organometallic synthesis. Alkyl halide with a metal give you organometallic reagent. And when you react with a ketone, in this case where both are R groups, you get tertiary alcohol. So when M, the metal, is magnesium, you get Grignard reaction. But when M is other metals like zinc, indium, tin, you get a Barbier reaction. This is an aldehyde, and this is an alkyl bromide. You throw in indium, you put the indium in between this C, Br bond, you squeeze in. This carbon becomes a terrific nucleophile. It attacks this delta positive carbon, push it up, you work up using water, you get an alcohol, secondary alcohol. So aldehyde, organometallic reagent, secondary alcohol. Ketone, RMGX, you get a tertiary alcohol. If you want to know more, you can research on this tetrahedral letter. Issue 42 you can download from NUS library and read up about it. It's always good to learn more and in depth, but do not force yourself. I think it's just being a responsible student. If you are curious to know more, always ask questions, do your own research, and after that, still not sure why, ask a lecturer. Okay? So good luck for synthesis, and that's all. Bye.